Hello and welcome everyone. Today I would like to talk about Fourier transformation in biomedical engineering and to analyze and to study biomedical signals. So first we're going to talk about what is a Fourier transformation to begin with and what is the application of it in biomedical engineering. Well, actually, what it does, it converts a signal from the time domain into the frequency domain, or from the frequency domain to the time domain, which help us study and analyze the signal. There's two types of Fourier transformation. There's the forward Fourier transformation, the FT. Okay? And there's the inverse Fourier transformation. And each one actually has its own purpose. So if I want to analyze or filter a signal, I'm going to use the forward Fourier transformation. Okay? So here for analyzing, to analyze, to filter a signal. Okay? In biomedical engineering, we apply that when we study signals like ECG, electrocardiograph, or EEG, electroencephalograph, the waves of the brain. I'm going to talk about this in more details for a bit. And I have the inverse Fourier transformation. I use it when I want to reconstruct the original signal or image, like in MRI. So it is the reverse, reconstruct the original, sorry about my handwriting, or original image or signal. So let's go through first a little introduction about the process itself. So usually as a frequency, there is some patterns that are not very clear. Okay? So this is, we apply the forward analysis, forward Fourier transformation to be able to deal with this noise, the baseline noise. Sometimes from the power line, we have 50 or 60 hertz, depends on the country. So we could remove all those noises and sometimes motions in the human body that could also lead to noise that could make the image not very clear. So we know that a noise has a specific range of frequency, and we could deal with it like this. But if we're trying to take an MRI case, when we have actually the MRI machine collects the raw data, the case space, it's a frequency, okay? And I wanted to convert it into something like space or positioning system to know each wave where it's come from, so I could control the brightness and the location of each frequency. For example, for an MRI, of course, as we said, that the device, the MRI, gives me the frequency, the case space frequency, but eventually I want a final image, an image that I could, as a human, when I see it, understand, because the human eyes can't understand the frequency. It needs something like an image, okay? An image of a brain, of a knee, a lung, something. Imagining like you're reading the note of music, but you can't fully recognize and understand or feel the music unless you actually listen to an actual music, not just reading the note. Pretty much the same principle here. So in MRI we have something called K-space, which is the raw material. It's something like this. So here we have KY, we have the Y and the X axis. Here is the X axis for the raw material. It would be something like this. For example, you're actually detecting the frequency, but this whole thing doesn't make sense. It's obviously represents something, but in the frequency domain. But as a human, as a radiologist, for example, that does not make any sense. So I want the Fourier transformation to convert it into an image. So I apply the inverse Fourier transformation. So I end up with something like this. For example, if I have a leg, this is a leg. Okay, this is the knee, two bones, for example. So that image, through the inverse Fourier transformation, it was converted into this image of a knee from the side that as a human I could understand and deal with it. So I could see if there's a bone, if there's, like, when I'm looking at a brain, I could see if there is a tumor because the density is different. So this is why we use the Fourier transformation, because we want things to make sense. So let's now go through a little math. As we said that the Fourier transformation uses the Euler number or complex analysis, which means if I have fx here, it has two components, a real part and an imaginary part. So it's real f plus I, the imaginary part, the imaginary of x. And the question is, why do I have two parts? This is of course a mathematical issue, but also it matters here. So the real part actually represent, at least when we study a signal in biomedical engineering, so simply it means how much of this signal is aligns with the cosine wave. Okay? It's used to represent the strength of my wave or my signal in each point. On the other hand, the imaginary part represent actually, of course, the same, how much the signal is aligned with the sine phase, but at the same time it helps me detect the spatial positioning in MRI, for example, or time and phases in ECG. So each one represents something. So if I get rid of the imaginary part, the whole image or the whole signal won't make sense anymore. We need the whole information to help us determine the positioning of each part of the image, also the power or the brightness when we talk about MRI. And remember that Euler number with the complex form is cosine plus I, the imaginary number, sine of theta. So the cosine or the real part tells me about the strength of my signal, and the imaginary part to indicate time and position. So eventually what I want to say that we use actually both forward Fourier transformation and inverse, and the inverse Fourier transformation, each one. So if I want to analyze or filter a signal, I'm going to use the forward FT. And if I want to reconstruct the original image or signal to make me as a human able to deal with this final image that is made of pixels, I'm going to use the inverse Fourier transformation. Hopefully this video was useful, and it's actually one of the most interesting topics in biosignals. All right, and hope you enjoy the video. Thank you.